Hello everyone. This video is going to cover a randomized block ANOVA, how to calculate it in Excel and what the analysis tells us. So we're still dealing with our corn yield measured in bushels per acre, looking at it from Nebraska, North Dakota, and South Dakota. The difference is that instead of having multiple data points in between the years or for each year, we're going to use the years as different blocks. So that's our randomized block. When we do this, we are going to use it's going to be able to answer the question of, is there a difference in the average corn yield per year by each state? And so our null hypothesis is actually identical to our null hypothesis if we were going to calculate a one-way ANOVA or a single factor ANOVA. So we're still just saying the average corn yield is equal for Nebraska, North Dakota, South Dakota, or the alternative hypothesis where it is not equal. So in order to calculate this, we're going to use our data tab and that data analysis tool. Again, this looks a little bit different if you're on a PC, but we've used the single factor, so now we're going to use two-factor without replication. Replication would be if we had multiple data points for each year. So since we only have single data points for each year, we're going to go without replication. And we want to make sure our data set is A2 through D8. Make sure that labels box is checked and that our alpha is 0.05 because we're going to use that 95% confidence or that 95%. And then for output, we're just going to go with F7 so that it's on the same page so we can see it. All right, so here is what Excel gives us. It gives us a summary of our data based off of our blocks, but then also based off of our populations. When it gives us our ANOVA, it's going to do it in rows, columns, and the error. So our rows are actually telling us the blocking variation. So that's the variation based off of year. And then our columns are telling us the between variation, which is between our populations. And because ultimately what we want to know about is that between variation between our populations, we're going to look at the p-value of the columns. So that p-value way over here is 8.8 e to the negative 6, which means we have to move that decimal 6 places to the left. So that p-value is definitely below 0.05. What that tells us is that we can reject that null hypothesis that they are all equal. So we now know that either they're all unequal or somewhere in the comparison is an unequal corn yield. So once we've got that figured out, we've got to go and do that Tukey-Kramer test, what we've done before. So there's a specific Tukey-Kramer test for randomized block ANOVAs, which is on page 528. So we're just going to create that lovely table that we have done before. And again, we've got to look at our sample mean differences. So we're going to look at the Nebraska, North Dakota comparison, the North Dakota, South Dakota comparison, and the Nebraska, South Dakota comparison. And we need to find our differences first, that absolute difference. Then we're going to need to find our number of blocks, so our B, our critical range. We're going to figure out what the outcome is and then what the meaning of it is. So, all right, let's start with our difference. So we need to find equals the absolute value of the difference in our means from Nebraska. Here's my average, so there's Nebraska, minus North Dakota. And we can close that and hit enter. So I-17 minus I-18. We're going to do the same thing for North Dakota and South Dakota, so equals the absolute difference between North Dakota and South Dakota. Subtract, you can see I'm doing that up here. Enter. And then our final one is the absolute difference between Nebraska and South Dakota. I-17 minus I-19. So there are my three differences. My B is the number of blocks. So how many years? Because my years were my blocks, so there's 6. So that's going to be the same all the way. All right, so now we've got to figure out that critical range. And we're on page 529 right now, looking at the formula 11.19. To find that critical range, we first have to find our critical Q value that we found in the single ANOVA, and it's also used in the two-way ANOVA with replication. So we're going to go find that critical Q value from page 852. And in order to do that, our D1 is representative of the number of populations. So D1 is simply 3 because we have 3 populations: North Dakota, South Dakota, Minnesota. Or North Dakota, South Dakota, Nebraska. Our D2 is actually a little bit trickier, and that's going to be the number of blocks minus 1 times the number of populations minus 1. So when we do that, it's actually looked at as B minus 1, little b, times, they use K to represent the number of populations minus 1. So our D2 is actually equal to number of blocks, which is 6 minus 1. 6 minus 1 times our number of populations, which is 3 minus 1. So when we do that math, we end up with 5 times 2, which is 10. You can also get that from your degrees of freedom for the error, which is 10. So our population times our 10, our population is 3, and then our D2 is then 10. So if you look in the back of the book on page 852, when you go across the top for D1 and find the 3, and then go down the side for the 10, you get 3.88 is your critical Q value. So now to figure out our critical range, I'll type this in. To figure out our critical range, we need to take our Q value, and we want to absolute reference that because we don't want it to change, and multiply that by the square root of our mean square error, which here's our error term, here's our mean square. So our mean square error, and again we want to absolute reference that. So you can see I-26 with the dollar signs, divided by our number of blocks, which is 6. And then we close it up, hit return, and we get our critical range is 13.09. Fill that down and it should be the same because our number of blocks isn't changing for any of them. So now we've got to look at our differences compared to our critical ranges. Remember, if our critical range, or if our difference is greater than our critical range, then we reject the null hypothesis. So 44 is definitely bigger than 13, so we reject the null hypothesis. 14 isn't too far above, but it's still above, so we reject the null hypothesis. And the same is true for the Nebraska and South Dakota data. So we reject. So all of these are rejected, which means that the means are different. So the means are different. So the mean corn yield is not equal between North Dakota, or Nebraska and North Dakota and South Dakota, Nebraska and South Dakota. If you're wondering why we did this compared to a one-way, there is a lovely chart in the book or not chart, but three reasons behind it on whether you should block or not. Does it matter? Some of the times you'll get the same result, sometimes you won't. If I used this same data and redid it with a one-way, everything would come out the same, except we would be unable to reject in North Dakota and South Dakota. So the difference is that when we put it into year categories, there is a significant difference between North Dakota and South Dakota. If we don't look at the year differences, then they say that we don't have enough evidence to show that. So here, putting it into a block form does make a difference. So the author of this text gives you 3 steps to look at. If it looks to be appropriate to block in a specific analysis, so if you have years or something where you just have one data point, begin with the randomized block ANOVA. Do it this way first. If the main factor is significant, so if this between variation is significant, reject your null hypothesis and keep going with the Tukey Kramer test and figure out your conclusions. If the main factor of the randomized block design is not significant, so if we would not have been able to reject that null hypothesis, retest it with a one-way ANOVA and see what results you get that way. So this is, again, how to use Excel on a randomized block ANOVA.